Or
So
which point? By the way, we live now, so nothing personal discussed. Uh, you said we are nearing what point?
okay, the in 2000,
Yeah.
a construction worker, just something, some guy totally irrelevant,
Mm-hmm.
can whip out a resume and say, I have this many experience and I'm expert in IT technology.
Mm-hmm.
That's the at the peak of the bubble,
I see.
and there's like such a huge shortage of people that anybody can get it. And we're kind of approaching that point. That was my point.
Yeah,
You see like a very bizarre parallel right now.
it's true. And at the same time, with the AI, we keep replacing our own things. So, by the way, I got into SageMaker,
Oh.
Amazon SageMaker.
Okay,
Yo, it's so good.
but okay. Also, make sure you look at Google Cloud Computer, Google ML engine.
ML engine,
It's even cheaper.
but same thing.
It's cheaper to run inference. I think they have better infrastructure.
All right, I'll check it out. Right now, we have credits for Amazon Web Services.
Oh,
Yeah, so that's what we start with. But we're eligible for Google Cloud as well.
you should go for Google one. I think I would bet more on Google if I get a chance.
Yeah. Okay. So we're gonna start with Amazon since we're already starting. We have money, and we have a year to burn all this money, right? So we'll do that, burn as much as we can, and then if anything, we'll just switch to Google.
Okay. The good thing is, if you make something for SageMaker,
Mm-hmm.
it's not very hard to convert a model into a TensorFlow one. I think right now the thing they're like, I think a safe bet is probably like this thing called TF estimator.
Mm-hmm.
If you just write everything in like static graph and TF estimator, you're almost guaranteed to run everything in all platforms.
TF estimator.
Yeah.
All right.
It's a higher level framework. So because I know Google infrastructure, like you don't have to do TF estimator, or you just do like things in very canonical way. Like all these platforms are converging into the same API interface, which is basically they ask you to give a model function, input function, output function. The shape are like it's converging
Yes.
to something. This is almost exactly the same.
Yeah, it's very standard.
So yeah, I think I take back my TF estimator. Is I don't necessarily have to. It should be okay.
But yes, the SageMaker supports TensorFlow, PyTorch, and MXNet. Those are the platforms we're going to start with.
That's a
But
lot.
yeah, but we're going to cover like as much research as possible.
But you don't have enough people to do that.
No, that's the problem. That's the reason. Goal is not for us to replicate every paper from the researchers. It's goal for them, for us to say, hey, here's the once you have your code running on your machine, put in a Docker and give it to us, so we can automatically deploy it. We can automate this whole deployment process. We don't want to replicate every single paper that people submit
Okay.
because that would be a pain. But we need to converge to that standard. How do we do that? And that's why we want to first 10 20 papers want to do 10 20 models want to build ourselves, like deploy ourselves to see how it's done, and then okay, so this could be automated, these parts could be automated, and this is what we should explain to researchers when they submit their models. Have some framework, but to find that framework we have to do it ourselves first. But yeah, the goal is have everything automated. Oh yeah. Where is the? How do you share this thing? Oh, there you go, links. Video embed YouTube page. Do you know how to share this thing? Do you get share link? The one that I post on. Click this.
Is that what you mean?
No, no. I mean, I want to share
Oh,
this link to other guys.
is there anyone else?
No, no.
Not
The
right now.
Willie might join us. That's why I wanna. Should we just beat this?
Oh no, but that's not a join one. Oh, here.
Okay, perfect. Totally missed that part. Okay, I think the Willie and Werner will join us online. Austin is not here today. Okay, so today we were essentially today we're trying to just wrap up the whole RNN.
Mm-hmm.
I like the logo. Can you mute your thing maybe? Or I can mute mine. Okay, cool.
Oh, why do I join? Oh, okay.
Yeah.
Can you do a summary of what happened last time?
The summary. So essentially, over the past two meetings, what we are doing. Last meeting, we spent a lot of time on trying to understand the beam search. Um, and the day before, we spent most of the time trying to understand the how to input uh, word to vec, and also we covered some beam search, right? And also some questions about the whole idea of the RNNs in general.
Architecture stuff, right?
Yeah, architecture. So I think Austin was the one interested in the word embedding. So yeah, um, today, have you touched anything? Or okay, how about you, Harriet?
Me?
Yeah, did you?
Touch anything?
Yeah, I mean the RNN wise, did you
It was just
work on
last
anything?
time when we were talking about the architecture.
Yeah.
right? Yeah.
Architecture.
So we were trying to understand mostly your talk, using your talk
Okay.
to compare it with our version of things.
Oh, I
right?
see. You're trying to
To-
understand
yeah.
attention. Okay.
We were doing a comparison, right?
Yeah.
Yeah.
Okay.
And also like that bi-directional thing. I think when I was like watching that YouTube video, no, like that video about bi-directional, I think I kind of understood it a little bit different from what Jake was saying. Because like he was saying why you add the bi-directional it was because the signals is weaker and weaker, right? And then so you have to go back and then you have to come back, right?
Mhm.
To kind of
Mhm.
it.
Yeah.
And then but then when I was like watching that video that I posted there, the this one that I posted here,
Mhm.
I think Andrew was like talking
Beam
if
search?
no. The bi-direction RNN around 7:07:01. I think it's like from my understanding, it's different from that. It's more about you. Um, what was it? I forgot. Okay, let's move on. What's I don't know. What's your understanding of why what is the why is it necessary? What is the need for bi-direction?
I was gonna say there's no need for bidirectional.
No,
For later
he was
research.
saying something.
There's no need.
It's if you look at the attention paper, I think you ought to also look at a follow-up paper
Mhm.
by some other guy who basically did ablation. Like when Bengio they published the original attention paper, it was a rush job. Like wasn't very well, I guess, tested out, but they achieved state of art. They're like, okay, and not that state of art, they achieved like improved by wide margin, and the architecture is novel, and they also stabbed a whole bunch of other things like reversed input that helps, bidirectional, and GRU, and they slapped everything there, and they achieved state of art, but it was not clear how much each of those addition was contributing to the improvement of performance.
Mhm.
So someone in 2015 did another more thorough study. What he found was bidirectional doesn't really help that much.
Okay.
So
Okay. Do you want to watch his video? What? Like I don't know. He was like saying something. He's gonna say.
We are watching that video that Harriet posted.
sorry, I couldn't get this.
It's just so close. Do you wanna play it? Maybe your computer is louder.
Yeah, but okay.
Maybe we can also share so William and Werner can see it. I'm gonna mute myself.
I don't know my computer is louder.
Oh, okay. Now it's good.
Okay, I can mute myself.
Okay.
You muted yourself?
To help the prediction with Y3. Now, one weakness of this
Yeah.
RNN is that it only uses the information.
For a
that is
second, can
earlier
you
in the
share that
sequence in
video?
prediction. In particular,
Screen share so the
when
guys can see as
predicting
well.
Y3, it doesn't use information about the words X4, X5, X6, and so on. And so
Okay,
this is
yeah.
a problem.
Yeah,
because-
okay.
Wait,
Now I remember. Yeah.
I don't get.
Okay. Now I remember. So he said why bidirection is because when you predict for say a Y3, you are only using information of Y1 and Y2, so previous one, but you're not using the information which is after this position.
Okay.
So
I
that's
see
why
what you're saying.
bidirection is needed. It's because you need to use on the previous data, but also the data after it.
I think,
After that sequence.
yeah, that's the point. I think you are more correct.
Huh?
I think you are more correct. Jake's comment has some. There's some. I think it's correct to an extent, but it doesn't solve the fundamental problem of basically forgetting as the sequence goes. It becomes very long. Like bidirectional doesn't really solve that. It only alleviates that in the sense that. Oh, it doesn't
Yeah.
actually. It actually doesn't.
Yeah, I guess it was so it's using information this way, but it's also using information this
Yeah.
way.
So even you have bidirectional, long-term things
Yeah.
from the left to right. It's still forgotten. All the information is still relatively concentrated around
Mhm.
the adjacent,
recent
more recent ones.
So sorry, Harriet. You're saying that the reason we're doing the bidirectional is because we want to know what's happening in the
After, because he was giving an example like for say like a sentence, right?
yeah.
Maybe the first like three words are completely very similar, but that thing is actually completely different context like later on.
Mm-hmm.
So it's a completely different, so that you're not really using that information
Right.
that is coming, that is gonna come afterwards.
So what you
It
say?
might give you very different outcome.
Right. So
Is
just to get the
is the
context.
speaker on?
Yeah.
Okay.
So just to get the context from the other side, right?
Yeah.
I see. So you have this one, like the Teddy. It's either Teddy Bear or Teddy Roosevelt, right? That's the example he was
exactly.
getting.
Yes.
Okay.
That's the great.
Yeah, fair enough. Uh, yeah, that was my understanding of bidirectional RNNs as well. Let me check real quick with the guys online. Willie and Werner.
Hey,
Where are
yo.
you guys?
Hello.
Oh, jeez, we have like today, whoever comes is like the dedicated group or whatever.
Yeah, it's like the.
We need a badge for this, man.
Yeah, this is like the group, right?
The group.
Have you guys made any progress, or do you have any updates to share?
I wish I could say something nice about that.
All right, sounds good. What about you, Werner?
No, not really.
All
Not
right.
vacation, so
All right.
There's a lot of promise. Next year is going to be spectacular. I can say that.
Why is that?
What?
He's using bi-directional, guys.
Because
Okay.
Using bidirectional, so you see into the future, right?
yeah,
All right.
yeah, sure that. No. Well, I'm doing next term. It's changed. I'm doing neural network course, and I'm doing a reading. It's going to be all neural network, all day, all night.
Okay.
Oh, nice.
Great
Yeah.
choice.
Yeah.
All right. So I guess since we are in this state again, let's in about an hour and a half, let's go through the RNN with the attention, whatever we have, the code, and like try to understand like everything. Are you guys really at least do a little summary and then figure out if we still like a little bit wrong somewhere?
Okay. Wait, do we need projector?
Here maybe. And just before we finish our session, essentially, to make sure we all understand like every single line in the code. That would be fair, right?
Yeah. Yeah, I guess, hold on. I suppose if you're asking like questions in that, like where Y hat, I was just thinking, I was going to get to that, where it should go in if it gets concatenated to H and attention. So yeah, I guess that's the only thing I could do is just, I'm assuming then concatenating Y hat with like where the attention, the context vector is put in. I guess that's the question I would do, and I would assume that's where you want to put it. So post active, yeah.
Question?
I guess that's a question, but I guess a confirmation question.
All right. So okay, let me do the. I'm gonna do the draw IO. There are a couple of questions that I also have that I'll ask you guys.
Sorry. Oh, okay. I need to go back.
All right. And then. So essentially, to figure out all the dimensions, that's my main concern. Werner,
what's up?
how are you? Where are you?
I'm good. I am at home. I just came back.
In Toronto?
Yeah,
Hey, welcome back.
thank you. So I'm still fighting with jet lag.
Came back from where?
I was in Taiwan.
Oh. Good for you, Werner.
Thanks.
Mm. That's
Are
where all
you-
the goodies are made.
Yeah. Food was good.
Werner, are you in downtown by any chance, or?
No, I'm at home. I am a Finch.
Oh, okay.
Neighbor.
He's your neighbor, okay.
Yeah. And Werner's my neighbor.
Werner's your neighbor.
Yeah.
All right, so you said the projector we can use, or?
Unfortunately, I couldn't
All right.
find the cord.
No problem, no problem. We can use just share screen. All right, so maybe I can share my screen for now with some of my questions. Um, Can you see my screen?
Yep.
All right, perfect. So what I'm doing is I'm putting this. I think this is the code we're trying to kind of nail. I'm gonna close this back. This guy. I also created this RNN flow chart. So it would be really nice if we could actually figure out all the dimensions and really understand
Mm.
where each line in this code. Oops. Model one step attention, like this, where it corresponds in this part in the graph. And then like add any other questions if you have any. Is your speaker on?
Okay, sorry. That's funny.
I think your microphone is also on. Can you press mute yourself?
How?
I think your video is also on.
All right. So what you do is
Oh, yeah, getting nasty feedback.
all right.
Someone need to turn off the mic.
What?
Okay, it's better now.
Yeah. So I guess this is the better version. I already started doing stuff. So the one question is the previous repeat vector. So I found this actually explanation of a repeat vector, and I found it very interesting. I think it actually explains what it is. Can you guys see my screen? Yeah.
Mhm.
Can I see a code real quick?
Sure.
1 minute. Where is it?
So this one is essentially defining all the global
So
variables.
The repeater repeats on Tx.
Tx is the size of input. How many LSTMs for the
Size of-
encoder?
And then where is this being used?
The repeater is used here.
Previous S.
And previous S is essentially this S.
Okay.
That is
It's
fed
like
into
coming
attention.
from left. Okay.
Yeah. So what we're trying to understand now is essentially this architecture. This is attention block, one step attention. This one right here.
So it repeats. Use repeater to repeat of shape MTS. And so that you can concatenate with all the hidden states. A. And all the hidden states. Okay. And you wrote confused here, isn't it? That's what you wrote.
Yeah. So I'm a bit confused with the whole how it's defined, right? So for example, if you look at the repeater, right? This is a class essentially in the keras, right?
So I would imagine.
So repeat vector layer, you take a layer and then you repeat it. It says you repeat input.
Okay. My question would be: does this add a fundamentally add one more dimension to the output?
So we can look in the code.
Oh, sorry. Can you go back to the? Okay. I think it does. Input shape, number of samples, features, and output shape. Oh, sorry. Yeah. Below, number of samples, and number of features. Okay.
Okay, so you say, okay, here's my model. I'm adding a dense layer, right, with the 32 inputs.
Yeah.
And then you say repeat vector 3 times.
Mhm.
So it adds dimension essentially.
I would think so. Based on what it looks like.
So yeah, my understanding was, I was trying to draw it. I'll try to draw it here, right? So essentially, you know, when you have a, if you look here, this S, right? So this attention takes as inputs the vectors 8, which is like Tx of m, right? And then it wants to it concatenates them with the S, which is the previous state.
Mhm.
So to do that, you gotta copy S like Tx times. So you can concatenate them properly. I'll show you in the next one here, right? So you take this S. How do you say S? State? Or what was the? How did they call them?
Yeah, I think it's essentially state stands for state.
Anyway, yeah. So let's call it state, right? So you take S from the previous post attention LSTM, the output of it. Then you do through then you pass it through repeat vector. So you copy it like TX times. And then you can coordinate them with each A. So then as an output you have this vector of S and A. But I'm still a bit confused what comes out of this piece of code. So how does the repeater works? So all it does is just it takes the tensor and just makes a new tensor by adding a dimension.
Yeah, that's what I think. Yeah. So it added a new dimension of TX items into as previous.
Okay. So do you guys follow online?
Mm-hmm.
I'll make it a lot bigger. So this is the code that is used for this repeater vector from our code. So essentially it just replicates, and this what we do next is the concatenator.
Well, actually, maybe I should ask, because the only confusion I had is why even bother with this repeater functionality. What you're just using one tensor and just keep on using the same tensor with all the concatenations. So my assumption is the reason it needs to do that is due to the particulars of having a compiled graph, and that it needs to be in a loop somewhere, in the loop of that compiled graph. So I assume.
He mentioned something about loop here.
Okay. So your goal is to you try to draw things from a list of items here, right? TX items here in particular. That each item consists of a attention on position. Some feature you compute from position I plus the previous state.
Mm-hmm.
So I think there's this inherent misalignment. Like you essentially this S is repeated for every item for you to you want to sum them up, aggregate them. But before you aggregate, your aggregation is a concatenation of something in position I and the previous state, st minus 1. So st minus 1 is repeated like tx times. One implementation is like how they do it here. I would agree, yes. They do this because they want to enable some kind of parallelism so that they don't have to write some kind of for loop explicitly. So the alternative would be to have some for loop in your code where you concatenate on the fly.
Mm-hmm.
I'm not sure that I'll answer your question, but that's
I think so. What I think it is, the reason that repeater layer is there is then you get to exploit the functionality that Keras has, all that it's wrapping. So yeah, that's what I assume. I think we might be talking about the same thing, but that's what I figure, because Keras can do all this stuff behind the scenes.
Yeah, I think we're talking about the same thing. So fundamentally, it is what it does is it tries to make things more static, so that it can probably enable parallelism under the hood.
Yeah, makes sense.
Okay. What's the dimension of our S?
I think it's a hyperparameter.
It's hyperparameter.
Yeah, it should be defined somewhere in the when you construct the graph.
Okay. No, it's not here. So as previous, I think
Yeah.
when you do the model, here's our model. Okay, S0.
What is that? N underscore S.
And
Oh, N underscore S. Okay, that's a higher. That's a parameter.
64.
64. Yeah.
Oh, what is that? It's just a
It's the number of numbers in the S vector, I guess. Number of numbers.
hidden
dimension
state
of the number.
size. Okay, hidden state
Because
size.
S is a vector, right? Then if it's a vector, then you gotta specify the size.
All right, so it says it is a hidden state. These dimensions are very tricky. Like you gotta really nail them.
Mhm.
Come on. Okay. So NA minus so the dimension of this S is essentially this.
So S
And
is sort of S is sort of like the S comes from essentially comes from the decoder part, right? So well A sort of comes from the encoder.
A?
Yeah.
No, the yeah, S comes from the post LSTM, so it's this guy.
Yeah. Okay. And A comes from the encoder part.
Yeah.
Okay.
So what's the dimension of our A's?
A is should be 2 times the dimension of the encoder hidden units. Because you're using this one is using bidirectional, right? Oh, okay, it's bidirectional, yeah.
Yeah. So it's gonna be what? 2 times of 1?
2 times of that's another hyperparameter, right? I was like I saw some I just saw like there was an N underscore A somewhere.
Oh, I see. Hidden state of bidirectional STM.
I'm not sure if it's 2 times or what, but it's either N underscore A or N underscore A times 2.
Yeah, maybe this thing is the keras wraps it around. So when you say an A, it's actually you don't have to multiply it by 2.
But okay,
Is there any
when go
concatenation
okay the line behind step 1. So
behind step 1?
Yeah, you were there. Yeah.
Here.
Yeah. Okay. So you first N underscore A gets passed into LSTM. So the first parameter of LSTM,
Mm-hmm.
I think it specifies number of hidden units, right? And therefore the number of hidden
Mm-hmm.
outputs. And then you wrap a bidirectional around that.
Mm-hmm.
So I would imagine the actual output will be twice 2 times N underscore A.
Yeah, makes sense.
But
Because we have it
I guess,
here.
yeah, okay.
We have it. Where was it? Yeah. A is concatenation of A
Yeah,
one
in
way.
theory, that should be that way. Okay.
All right, so I'm gonna say 2 times an A, right?
Yeah, it should be, unless we have new evidence that says otherwise.
Okay, for now. So then this after concatenation, it's gonna be
Uh,
and that's plus 2 times an A.
yeah, I would think so. So then, okay, then there's the opportunity to verify if that the dense layer actually is that, or
This.
yeah, the includable dense layer,
Mhm.
or maybe that's kind of hidden by Keras, you may not even need to worry about it.
They actually specify this denser 1 and denser 2.
Okay, so because they're using
Oh,
Keras, you don't need to
yeah,
worry
you
about
don't
it.
see it.
Can I? Okay, can you? But this is not actually where dancer A and dancer B are
Use?
being instantiated. Yes.
No, this is where they instantiated.
So
so-
this construct. Okay, you still need to call that somewhere. Dancer
Yes,
1 and
yes.
dancer B.
It's here.
Oh yeah, then connect everything together. So you don't really actually get it specified explicitly the dimensions.
So when I was reading it, their explanation was you want to make sure in this network, you're reusing the same weights across the network. So every time you like, let's say call this jam, you're not initiating
Yeah.
it's from 0 again.
Yeah, if you use repeater,
Yeah,
that should do that. Right?
yeah. That's why they initiate it like globally.
Okay.
And then they use them separately.
You're talking about S, right?
No, I'm talking about all these layers.
Oh yeah, okay.
The repeater,
So S is
concatenator, and
okay.
everything. So yeah, I'm a bit confused why they need 2 dense layers and how they actually using them.
Why
'Cause-
do you need 2 dense layers?
Yeah, because all I see here is just 1 dense layer. And here they pass it through first one, and here it says to get intermediate energies, and then propagate through a small fully connected neural network to compute energies. And I'm like,
Because that's the original formulation. So through alpha is now the final attention weights. So you still have to go through a layer of nonlinearity. That's originally how it's formulated.
mhm.
Just well, whenever you see these, it's just basically endowing the network with more power. I guess. Approximately more complex things. You might just try not to do this, and maybe the results will be similar.
Right.
Yeah.
Okay. So we have this dense layer 1. So let me try to. I don't know how to.
The difference between the 2 dense layers, the first one outputs 10-dimension tensor, and then the second one is a 1-dimension tensor, and then the first one is 10H, and the second one is ReLO. So
Yeah.
it's bringing it down to the single vector that we need. And I guess for whatever reason, that's the better way to do it as opposed to just 1 layer.
But why can't you just like specify? Okay, just do directly answer 2. So
Yeah, well, yeah, then we got to dig into the literature, maybe, and for all we know, it's like experiment showed, right? Just empirical, maybe.
I'm sorry, I missed that part. Were you saying why don't we do what?
exactly what you asked. Like, why do you need to do it?
Yeah.
Yeah, we assume they have their reasons.
All right. All right. So I just want to make sure I. No. Oh my.
You just close that.
No, you see I'm using Opera because my Chrome is acting weird, and I'm used to shortcuts with the Opera. I mean with the Chrome, so every time I'm using the same shortcuts, it just freaks out.
Do you find that machine learning mastery guide good?
Very good.
Very good. Hayden said he's the exact episode is happy.
Who?
Hayden.
Who is Hayden?
A guy came to the company to interview for the director position. Hayden.
Well, because he's a competitor.
Huh?
They produce the same kind of materials. Of course, he's going to say that.
Okay, good for him.
All right, so I just want to make sure we understand these dimensions properly. So we have this is coming in, right? These are dimensions coming in. and outcome the 10.
Mhm.
Whatever.
Mhm.
I have decided this paper.
Oh yeah, you sent it.
No, not that one. Another one. It's this one. I just. I have
Okay.
five. This is
You,
final.
I forgot to send you a message. Can you, whatever you sent to me, can you repeat that on PDL's channel?
Right, 10.
Just like, because you know both of them. You know Philippe.
Yeah.
Right? This is the size of this network, right? I mean, this is the weights, dimensions. Could have drawn more, but
Is it? Yeah. Correct.
all right. So this is here, and this guy is gonna be 10 by 1, right? Now the output. What would be the dimension of output?
1.
By what? Is it gonna be vector or just integer?
It's a vector of size 1. Because the output of the tensor is always a vector.
Yeah, but
I think the second, like the length of the vector is probably tx, isn't it?
You mean for tensor 2?
Yeah, that's the, hold on. Oh, wait, hold on.
because we're passing it through
Then
softmax after that.
it wouldn't make any sense. I think it's 1 thing.
Yeah, the softmax, the activator, right? That should be, hold on.
But wait, at this point we haven't passed through the softmax yet, right?
No.
We haven't. Okay.
Yeah.
So shouldn't be like each alpha is just one scalar, and you have px of them.
Yes.
Oh, actually, this is kind of complicated.
Okay, so I'm not following. Could you explain what's happening? Oh, by the way, you can also go to the. You guys can all open the same document, and you guys can edit it. Let me see if I can share the link. File share. You can edit.
Was Dave McDonald here during the last event?
Hmm?
Dave McDonald?
No.
Okay.
So each S, I guess the dimension then is not just one dimension, right? Vector. It's going to be two-dimensional vector for each S.
Okay, hold on. So we're talking like the assumption is that we're ignoring batch sizes here, right?
Yes.
Across the board.
Yes.
I would think it's one dimensional. Maybe for the alphas.
For S.
Oh, for S it's, I think it's still one dimensional. How come it's two dimensional?
Okay. Yeah, makes sense.
Okay.
That's what I would think. I would think that it would be one-dimensional and alphas are both one-dimensional. But when we do that, then our dimension of a denser 2, the output is just 1. It's like an integer.
Yeah, that's what I think.
And then we're passing it through softmax. Oh, we passing across like all of this softmax, right? We're just taking the highest one out of all of this.
Should have TX at this point.
Yeah. We have TX of this dense.
But hold
outputs.
on. Does that mean actually denser 2? Oh, wait. Can we see the code again? The denser 1, denser 2. Can we see how actually denser 1 is plugged in? How answer denser 1 is being called? Denser 1 is the concat. As previous. Actually, something doesn't look right. So A, did we miss something? Because in the actual implementation, this thing is only run once, right? It's not repeated TX time.
The one step attention.
Yeah.
Here's a model for no, we repeated TY times.
Oh. But we repeated TY times. But that's for each output. But for each input, sorry, for every time you compute one specific
Yes, every time you compute.
TY, you don't again repeat it TX times. You actually just calculate everything in one go.
Yes.
So that means there's a dimension of TX. So by the time you go to softmax, you have TX items.
Yes, like based on this graph, looks like it.
And then, but can we see how softmax is computed?
Softmax, I think it's activator.
And then, so that implies energies already has TX items.
This here, right?
Right.
What you're saying, this one implies there are 6 of them?
Yeah. Right.
So, okay, first let's look at the activator, the way it's initiated. Activator is a softmax activation. And
Yeah.
they use their custom softmax.
Okay. Okay.
Okay, so, but
So in the softmax, the input is TX item, output is one item. It's good.
say it again. Sorry.
Oh no. Actually no. What's the input and output for a softmax? The softmax is input is TX item,
And
but output is also TX item. Right? It's just like input this many this many things, output is still this many things, but just that the shape of the distribution has changed.
Okay, remind me of what softmax does again, because I'm lost here. Maybe I'm not seeing it properly.
Yeah.
Softmax.
Just the regular soft. Okay, we can do that as well. But the regular softmax.
Okay, let's just do the regular softmax.
Yeah, that's exactly what I was saying.
Oh,
why
okay,
you
I
have
see.
three things,
Yeah.
and its shape got kind of squashed. It's like it reduces it into some kind of winner take all situation where the biggest item, like in this case 2.0,
Yeah,
becomes the dominant one in the output.
I
I
see.
think that's essentially what softmax does.
I always got mixed up between softmax and the other one. What's the other one? That
Which
we were
one?
talking about? There. Softmax, there's another one which is very similar to this.
To
one.
softmax?
And something else. Softmax and
Sigmoid.
Yes.
Oh,
yes.
sigmoid. I see. I
Yes.
see. Yeah,
I
yeah.
think they're kind of close, right? Similar.
Well,
They start with S.
Sigmoid is operating on one item. Softmax is collectively operating on n items, each having an impact on the other, so that the output is the one winner.
So
Essentially.
then softmax is like normalizing on sigmoid?
It does more than that.
Huh? More than that?
Normalizing on sigmoid. Yeah, I think you're right, actually. That's what softmax does.
All right, so I'm just gonna say to the definition of this guy.
I'm tired, but I can tell you actually.
Oh, okay. So we have dense outputs for each one of these guys. So I'm just gonna make another one just to demonstrate.
Okay, sorry. That's where my hesitation. But in our implementation,
Mm-hmm.
I think it was wrong because dancer 2,
Mm-hmm.
I suspect the shape is actually
Its shape is what? Not one?
okay. It's weight matrix. The size of its mirror weight matrix is sorry, but dancer 1 is sorry. I'm looking at dancer 1. Dancer 1 is looking is that number like n underscore s plus 3 times n underscore a. That's one dimension, and the other dimension is 10.
This one, right?
Yeah, yeah. But the
But that one is 10 to 1, right? Dense.
yes, but okay, okay. It's actually yes, you have 10 to 1. I don't know, it becomes 1. But in actual implementation, you don't repeat because there's no explicit for it. You don't repeat it tx times. It's calculated in one go.
Which one are you talking about?
Okay, there are tx of the softmax, right?
TX of no. There's just one softmax.
No,
That takes all the denses.
okay, the input of the softmax, there's tx of them.
Input of a softmax, TX of output of dense.
Yeah,
twos,
and
right?
then the output of the softmax also tx.
Yes.
But in the code, you don't see tx. Something gets repeated tx times explicitly.
Oh, here, right? This is what you mean.
Yeah, so the energies,
Yeah.
by the time you get here, there's also a dimension of tx.
Yeah, but how?
That's what I'm trying to figure out. Okay. Tx. So that actually means through across the board, like the output of the tensor 1, it might actually be 10 times tx. It might be actually 3-dimensional, like if you count the batch size, but we're not counting the batch size. So it's 2-dimensional, 10 times tx. And
Okay,
then
so
the output for tensor 2 is still 10 times 1 times tx. Then it only makes sense that way. Then you have in energies you have tx items, and then you can pass on this energy on to the next phase.
okay, so here it says A. Its shape is TX times 2 and A.
Okay, that makes sense.
So we have to go back here and say each A is then, what was that? TX.
Okay. It's not each A. You only have one A. So it's.
Oh yeah, you're right. You're
yeah,
right.
So there's a misalignment like in here where in actual implementation, this entire thing is calculated in parallel in one go. But in here in the diagram, we kind of separate them into individual things,
Mm-hmm.
which might lead to the impression that we're calculating them individually, but it's actually we're not. We're doing it in one go for some reason.
But still, it should be TX of them here, right? Like this softmax should accept TX of them. So in this case, for one step, we are passing TX of them.
Okay.
Of
In
A's,
batch,
right?
in
Yeah.
order. Okay.
Yeah, and that's what we use the repeater. So we match this dimension.
Right.
TX. Okay, so let's brief. To be This is gonna be this guy's dimension.
You mean the output of S?
Yeah,
S oh, sorry, the I don't know, S previous.
yeah.
M times TX. Yeah, okay.
And this one, just to make sure, also MX, TX, and NS plus Q and NA, right?
Right.
Okay,
And then the energy.
yeah.
So that is not even.
It's gonna be a 10.
Well, I think this is gonna be 10 times TX.
We're gonna keep M as well. Just,
M is the batch size.
yeah.
Okay, sure.
It's gonna be TX and 10, right? And TX.
Maybe, yeah, either way.
Yeah. Well, I'm using so.
Then this M times TX times 1.
And this one is gonna be the same dimension, right? And context. Okay, finally the context. Context has its own formula actually, which is this guy right here.
So if there's sum, then there's a reduction in dimension.
Yeah, but we still have TX of them, right? Right.
No. I think
It's over TX,
This
yeah.
is when you actually eliminate TX because you're aggregating over TX.
Yeah.
So this is when TX disappears.
Okay.
I think.
Oh, I see. I see. So we're gonna end up with just M by 1.
Can we check the
Dot over?
definition of
Dot product.
X is equals to 1, so it's doing dot product on the first side instead of zeroth dimension, which in the first dimension. All right, so it collapses the TX dimension, but I think. Oh, okay. Can you go back to it? I can scroll down to the. Yeah.
Daughter?
Yeah. So you have the MTX1. So yeah. Yeah. Okay. You're right. So there's just one.
Yeah.
Should be one.
Okay. So here we're just gonna say after the softmax, this guy is gonna go to our context. And how do I specify all these dimensions?
So the context has a superscript T. That superscript T is actually refers to the time T in the output sequence, right? Time T of the output sequence.
Times T?
No, time like at time T of the output sequence. So that's where the superscript comes from. So you have Ty of the context.
All right. So you're talking about this graph where I'm working on, or here?
No, the context to the right.
Mm-hmm.
This diagram has a superscript T.
Yeah.
That T refers to a
Decoder.
time of the decoder.
Okay. Because yeah, we have another T here.
Mm.
Yeah, those T's are confusing. Okay.
I like the original paper. The original paper is very simple. It's like anything that refers to the encoder is I. Anything it refers to the decoder is J. So the original context actually makes more sense. I think Andrew kind of like modified it somewhat.
So this output is 1 by TX, right?
So,
And finally, our output is just 1. Right?
okay, yeah.
Okay. Okay, so this is our context, and this is done in the loop for no. that's what happens. Uh, this is for each INTYs or something. This context is then fed into the next LSTM. Okay. So our pre-attention bidirectional LSTMs, they accept vector, right, as an input.
Mhm.
But the context, the post-attention LSTM accepts just the floating point.
That seems to be lost.
Hey, Werner, you're still there?
Yeah, I'm here, but what happened?
Yeah, they cut out.
Oh,
I messaged. I can't message on Slack. If you can maybe message them there in case they, because I don't know if anybody's paying attention to the chat here.
okay.
Hello?
Yeah, I restarted my
Oh.
folder if you like.
Oh
Hey,
yeah, Iogen's computer froze again.
Oh,
So,
get a Mac, man.
yeah,
Stop using Windows.
that's the maybe the problem. I wouldn't recommend Mac though, because it's very hard to do deep learning with Mac. If you wanted an external GPU,
considering buying it. No?
it's not very. It's just not deep learning friendly in every way.
You're only going to SSH, which is fine.
Oh man, okay.
Fair point.
So let's move on. Should I share my screen or what?
Yeah.
Okay. So what I was saying, okay, what we were saying was context is a scalar, like through our derivation. So we're just trying to verify that in the original paper. It looks like a scalar.
Or just the code.
Yeah, it looks like a scalar to me. So you get a scalar for each timestamp. And then, yes, Ci is a scalar, is a sum of all these things. And then you get a scalar that is your, so how do you use Ci? You feed them into a nonlinear function, and along with the previous state and the previous output, and eventually you get the state of your hidden state. That feels a little bit weird. How come you end up having a scalar? But I don't have the code, so I guess I'll have to work with that.
Again.
Yeah.
This version 4. So we are looking at the model. By the way, I muted myself, so you're
Okay.
first film, right?
Can you guys hear Arjun all right?
Can you say something again?
Can you hear me?
Yeah, you're quieter, but yeah, you'll have to just speak up a bit.
All right. Let me put my mic on, I guess.
Sure. Then I'm muting myself.
Can you hear me now? Is your mic on?
Feedback.
All right. Okay.
Yeah, no, it's good.
So we were. Oh, shit. Just want to find which version we were working on before. Not this one. Another one. Yeah, this one. Close this guy. Okay, so we look at the model, right? We want to see the decoder input. Here, post activation LSTM cell.
Wait, what? Oh, it's LSTM.
Yeah.
Number dimensions. Okay, simple enough.
So
Yeah, these two make sense. So post number of hidden states, and then you have a final output layer, whose output is the number of words in your vocabulary.
okay. Post attention, and this is the softmax, right? Essentially. Is this a dense though?
And this should be taken a combined input of S minus one, Y minus one, and CI. So post activation of LSTM cell should take three things as input based on the original formula.
Okay. First, let's.
Yeah. Okay. Yeah.
Let me quickly add this dimensions so we have records. I'm gonna move guys, but here. This dimension. You stay where you were. Okay, so let's make another one. I'm gonna say post first here. And this guy's definition is this. And as an input, it takes exactly that.
Takes what?
The context.
It not only takes, it shouldn't only take context, it should take context plus the previous state. That's my understanding.
Yeah. So it takes this and we did not. We skipped that part.
Which one?
We skipped the concatenation repeated vector. So we started from here essentially. I'll add them later, I guess. But for now, we need to say that this guy also takes in as t minus 1, right?
Yeah, it should. And optionally, it should also take y t minus 1, but let's see.
y t minus 1? I don't think it does the y t minus 1. Here's the graph. for it.
Optionally, you don't always do that, but
No, it could, right?
you could. It's called teacher. Like some formula like they do like teacher forcing. Then you need y t minus 1.
Okay, that y t minus 1. What do you do? Do you concatenate with the c with the context?
Yeah, it should be just like a simple concatenation.
Okay.
But
Oh, what?
yeah, let's see in the code.
Okay, let me just add this dense layer after that.
Sure.
Oh no, it's called output layer. This guy takes the output of post LSTM and oh, just the softmax, right? Softmax over vocabulary size.
Mhm. Well, yeah. Explicitly just adding something.
All right, so the post LSTM's output is then the dimension of a vocabulary.
No. Post LCTM is the output is still n underscore s. So the way it works is by the time you got to here,
Mm-hmm.
you still have S is essentially an encoded state of everything that has happened.
Mm-hmm.
And then from this time on, you use st minus 1. You use this output in two different ways. One is you directly send it to
Next one.
to the output layer to produce the final results. In this case, is a vector vocabulary size.
Mm-hmm.
Each vocabulary is a probability. And then also you use this to feed that back into the next stage. Because remember, at the very beginning, we use st minus 1 too.
Yeah.
So I think it has two
Okay.
two uses.
So our st minus 1 is dimension is ns and 1,
Yeah,
right?
that should be exactly that.
So it's not this that's being passed then. Move it here a little bit and we can say that the same thing is being passed here, right?
Right.
Uh, say here. Now, this is the dense layer with the. Okay.
This is essentially the dimension. I think the function of it is just basically do a dimension change, so that it's the vocabulary size. Well,
Here.
NS. No, I think it's just vocab size 1. Because by the time you get here, like NS
Is it the input?
it's a dimension change. So it's dimension change from n underscore s to vocabulary size.
Yeah, but the input is going to be ns and vocabulary size, and the output is going to be vocabulary size 1, right?
Right. Yeah. And this this is essentially and s vocab size is essentially the size of the internal matrix.
I just want, I need to find a better way to describe what each one of these.
W equals W.
This?
No.
Yes.
Yeah, this one.
W
This is
equal?
the internal, right?
Yeah. These are weights of the dense. Okay. And this is going to be vocabulary size with the softmax, like the probability essentially. That's probability. Okay. Make sense, guys?
Do you guys have any comments?
I can't think of any. I was just trying to go through the debugger code and see if I could confirm the dimensions, and no luck. So
Okay.
okay.
It's a Keras model, right? Is there any part in the code where it does like a model.summary?
Yes. I can show you.
Maybe you could take a
Oh
look.
yeah, wait. Yeah, does the summary tell us?
But maybe that could tell you.
Let's
one
stretch
thing.
it. I cannot stretch it. Okay.
Yeah, can you click on
Hold on here.
click on this?
Oh,
It's
okay.
fully expand.
So tell me, where do you want to go? Dance.
To the
Start from the very beginning.
yeah, just the very hard thing. So 30 would be the length of the TX, the maximum length of the input sequence.
Yes.
So 37 is the vocab size.
Yes.
So S0 is another input layer. So you have two input layers. Have two inputs. And then when it goes through bi-directional, what happens?
I just want to make sure that 37 is the vocabulary size.
You can't, like, I don't think it's encoded. It's written explicitly anywhere. Yeah. Because XO, what is XOH?
Machine vocabulary. Yeah, you're right.
Oh,
Wait a second. Data sets. No.
and so in there you can also see like TX is equal to 30 and TY equals to 10.
What were you saying?
The code you were at, like TX equals 30, TY 10.
Yes.
Okay.
So TX is the input, which
The maximum length of the input.
yes, maximum length of input, and TY is the maximum length of the output.
Yeah.
X, Y, T, O, X, T, H, Y. This is human vocabulary. And this little guy is in utilities.
Well, you don't have to look at it because like it prints the thing. Like
Yeah. Okay.
the next right. Yeah, right.
O X shape. I'm not sure why it's 37. I think it's a human vocabulary.
It's a human 11. Yeah, okay. Then 11 is the machine vocabulary.
Yeah. Okay. Yeah.
37 is like alphanumeric.
Yeah, all the
thing
letters and
plus spaces.
plus spaces. Yeah. Okay. Cool. That
37.
makes sense.
S makes sense. It's actually
Hidden
64 is N underscore S. And then bidirectional 3064.
All right.
Shouldn't be like 31.8.
Bidirectional STM 64.
Oh, wait,
It's 2 times 32.
2 times N underscore A, right?
Yeah. And
N
A,
underscore is 32.
was it 32?
As far as I remember.
Yeah, you're right.
And then, so that's why, okay, 2 times 32, and you repeat it. When you repeat it, the dimension doesn't change.
But we repeated 60. We repeated TXM, which is 30
Oh,
times,
TX,
right?
okay. So originally it was 64, now it's 64.
Originally S0 was 64, right?
Right. And
Now,
you repeat it,
yeah.
64.
Now they're the
When
same
you
dimension.
concatenate, it's N underscore S plus 2 times N underscore A.
Yep.
That's 128. And then
Dense 30,
Yeah.
10.
but you don't know which one this dance is. Okay.
This is the first dense. So
Okay,
this
first dense.
30 and 10, right?
Okay. 30. to 10.
Listen, what happened with the 128? Let me look at the graph.
Where does 10 come from?
10? It's the definition of dense one.
Oh, okay.
So wait a second. So here's our dense, right?
Okay, that's 1. Okay.
We
So
take
yeah, it essentially does a dimension change from that dimension to 10, like from the 128 to 10.
from
Yeah,
128.
because the input is like n underscore s plus 2 times n underscore a, which is
Yeah.
128.
Yeah.
And the output
It's
kind
10.
of is effectively squeeze that down into 10.
Right.
10 odd numbers. So 30.
So this dimension in brackets is the output of it?
Yeah. Because you also have tx.
Okay. And this is our inputs, right?
Yeah, it should be. Yeah.
So it's 128 by 10. This is the weights.
Should be, yeah.
All right.
I think so.
Dense 2 is going to be 30 to 1. Okay, so from 10 to 1.
Mhm.
Just like we had before. Okay, so what were we saying with 30 again? 30 was
tx.
TX, yeah. Okay, attention weights. Activation. So this is this guy.
Mm.
Yep. So it is 30 to 1.
Mm.
And 64 was our.
So this is where oh, wait. Oh. What's this?
I think this is a hidden state of a post LSTM. This S.
Is it? But how come when you do a dot product, then you all of a sudden you increase the dimension?
NS.
Yes, but if you look at the definition of a dot product,
Definition of that product.
dot, it doesn't really do any additional thing. How come? Like, where does 64 come from? Yeah, it's just a dot product. It shouldn't. The dot product itself shouldn't change the number of the dimensions. It shouldn't change the number of dimensions. It should be like just clamp down a lot. Just basically reduce one dimension to 1. In our case, it's reduce the tx dimension. Before that, it was tx. Now it's 1.
But where do we pass this dot?
How come it becomes 64?
Did we miss dot? What was the dot? Activation softmax. Okay, maybe.
Did we miss
Yeah,
the dot?
it was
No.
here, right?
Yeah.
Is it a context that was a dot product for us? Let me look. Now here's the model. No, it's in one step. Alpha. Context, yeah, daughter.
Yeah. Okay.
So I'm gonna say dot axis 1. Okay, but we take 1 over tx and output comes 1.
Okay.
But why do we have 64 now, right? That's what you're saying.
Yeah.
Is it because we have ty is not 64, ty is
10.
10. It's not that.
So that's definitely like n underscore s, right?
Yeah.
So how come this appears all of a sudden?
Let's see where dot product is initiated and how we use it. Oh, wait a second.
Huh?
You say, oh no, for T, I know it's not that.
Carry.
It's not that. We just get the context and the dot is inside. So it's here.
Can I see the activator? What is activator?
Activator.
Oh, activator is just activation. So you have dancer 1, dancer 2. and reach dot product. Okay. Like 64 disappears all the time.
$64 and
Anyway, keep going.
so now our context is 64.
Yeah.
So it's not a
It's not a single. Yeah, that's why I was thinking weird. It's like by the time we got here, it shouldn't be just like single number. Otherwise, the power of like the information you store is like would be very little. It should be like more than one thing. So C is not a scalar. C is a vector.
Yeah. So
Hey,
no, it doesn't give us much. So yeah, the C is going to be a vector. Maybe this one will give us some info. No.
okay, fine. C is a vector.
Okay, so here's the context, right?
Yeah.
Here's the dot product, and then we summing them.
Yeah, if you look at this, you would think context is a scalar. But wow, all of a sudden, this new dimension emerges.
Yeah, but these alphas, each alphas are vectors, right? So
Okay.
what happens when we sum over vectors? It's a product of vectors, right? Dot product of vectors. I want to see how they implemented this guy. Context. Context Dlrl takes alphas and A. Dlrl. This guy. Here's the definition of that product. Look, if applied to a list of two tensors A and B of shape, batch size, and n, the output will
Yeah.
be a tensor of shape, batch size, and 1.
Mhm. That's what I would imagine. Yeah. Okay.
So maybe the dimension that we are reducing is not that we thought the TX.
It should be TS. Well, like how?
Yeah,
That makes sense conceptually, but actually, it's one is like the TX dimension. Basically, using TX dimension. Wait a second. Alpha A. Wait, when you do a dot product, oh, how come there's only one parameter?
What do you mean?
Because you would do a dot, there are like two things. You do dot product.
On alpha and A?
But those are, yeah. Okay, alpha and A. Yeah, there are two things. Alphas and A. Alphas, plural.
Yeah, because we are going over each one of these alphas.
Okay, alphas.
And just one A. Okay, where is this one A is coming from?
A is how can we come up with this stuff? Okay, A is A is the activation of something. A,
Oh, we're passing A for each step.
A hidden state output of the by LSTM.
Oh shit. So we take output of one guy and we then pass it through attention and then we pass it directly to a dot product.
Yeah.
Okay. All right, so we passing through attention, we're passing A's of every single bidirectional STM. And then a single one we're passing directly through, like bypassing attention network to that one.
Yeah,
attention.
okay. Alpha essentially is a attention weight, right? Alpha is essentially means like among all these things from the encoder, from all these timestamps, how important is the alpha item? So we have like TX alphas, and then you use that weight to multiply the actual output A.
Right.
That is the final outcome, and then you I guess you sum them up. So alpha itself is just like a importance indicator, and then you use that to time AI at each step.
How many contacts do we have? We have TY of them. Because I would assume that we have different number of alphas, right? We have TX of them, but we only have TY attentions. And this is where our 64 is coming from. Dimension. Come on, stick. Yeah. Okay, so we're removing, yeah, so in this case, we're multiplying 2 times NA and one-dimensional softmax. That's why you got 64? Yeah. Damn.
Okay. Okay.
But
I can take that. Okay, that makes sense.
yeah. But I'm kind of confused that we don't have the A's and the softmax outputs, they don't have to match with dimensions, right? because we have TX of the softmax output, and we only have so each alpha is applied to 64 of them every time. Each alpha is multiplied with 64 of them. Yeah, that's what I would assume. Yes. Yeah, and then we just
attention weight.
reduce the TX dimension.
Mm-hmm.
All right, so the output is going to
Okay,
be
I
64.
think it all makes sense now.
I'm not going to say 64. I'm going to say 2 times NA. Okay. And
Okay. Sorry to interrupt. I'm reading. So someone said the
Mhm.
sigmoid function will squeeze the error of your model at each layer by at least a quarter. Do you know why?
uh,
Can you say?
where is that?
So it says, so the sigmoid function, activation function, during the backpropagation process, it will squeeze
Yeah, because
your error.
because the gradients are small in sigmoid.
Gradients are
Mhm.
small.
If you look at the shape of sigmoid function and you look at a gradient,
That's
the
the derivative.
gradient is very small.
Oh, okay.
Yeah,
So
it's
smaller
it's
and
it's pretty
smaller.
it's only it's tiny even at its peak. So gradient is in here. And if you fall anywhere from here to here, the gradients are very small. That's why you use value instead of sigmoid, because sigmoid tends to give you it tends to exacerbate the vanishing gradient problem just by the nature of the shape.
But these values are the data themselves, right? Because you're
What do you mean value?
because these values, you're actually transforming these raw values to data into a value between 0 and 1, right?
Yes.
So which means that these are actually the data themselves, right?
What do you mean data?
Like the raw value, the input value. Right?
Yes.
Yeah. So these are the value themselves, right? And then so which means that your value, if your value is actually bigger in absolute value,
Yeah.
the gradient is actually
Yeah.
lower.
Right.
But how is that related to error?
Can you share that page?
This is okay. Latitude here. When you do backpropagation, you're talking about derivative sigmoid, right? So when you're talking about derivative sigmoid, that's the error is computed on. Oh, sorry, the derivative is computed on the error. So I think I'm not sure about. I think it actually means. Okay. So when maybe what it's saying is when you squash the function into 0 to 1, you could have a very large error. Say you could have like if your real value is 1 and your actual value is 3, you could have the two difference of t. But now it's being squashed. Everything being squashed from 0 to 1, which means the magnitude of your error becomes smaller. Maybe it's what that, but it overall, either on derivative or on the value function itself, it has a diminishing effect. It scales things down like at across the board.
Just remind me again, when we take the sigmoid activation function, we're taking it on the are we taking it on the error terms or actually the
Error.
input value?
When you take derivative?
No. The
No,
activation
you
function.
take it on the output of the
Input, so the input value.
No, it's usually applied sigmoid right after you've done the
Yeah,
neural networks.
the outcome of different layers, right? Input
One,
of
one
different
layer
layers.
is basically a linear combination of input.
Yeah.
After
and then
you've done
take
linear
the
combination,
activation.
then you apply signal.
So then how is it applying on the error then? Not squeezing the errors, it's squeezing the
Well, when we do back propagation, you start calculating the difference
Okay.
between two values.
I'm still a bit
Sorry to interrupt.
no worries.
It's fine.
Next time you ask a question, could you share that page that you're
Yeah,
discussing?
yeah.
So we can all look at it. When we look at the context, right? We have ty of the context, right? But when we compute the context, we go through every single alpha of tx. We have tx of alphas, right? You see what I mean?
We have alpha. The total number of alphas, I think, is two-dimensional.
The total number of
So
alphas.
for each, okay, so for each item in the output, and for each item in the input, you have an alpha. So it's basically saying, right now I'm outputting let's say the sixth item here,
Right.
and how important is the first item to me?
Yeah.
And how important is the second item in the encoder? How important is the second item to me, the encoder? How important is the third item to me, or encoder? For those, you have TX items.
Right.
And then you move on to the next thing you want to output. You have TX items again.
I see.
And then so it's like TX times TY in total.
So how many if we were to write it with the full loop, right?
Oh yeah, okay.
How
So
would that look like?
In our case, in the for loop, every time you iterate over only one thing, right? So one thing, like you only within this loop, you only care about.
For that attention, you mean?
No. For a output, okay, you have, let's just say we use J as the index for the output.
Yeah.
For each item J, you have TX items you need to attend to.
Yes.
So in theory, everything in the for loop, every time you run a for loop, there should be TX alphas.
TX alphas. Okay. Yes. That makes sense, right?
Mhm.
But when we have this context, right?
Yeah.
The one that we're computing right now. I'm trying to see where is that loop. Like if we were to write it with a full loop, this context, it would be for i's in TX.
Yeah, I think so. You mean if we don't do it in a parallel fashion and just like calculate one by one? Yeah.
Do all of this at the bottom, right? Do all this denser, do all this concatenation, all this.
Yeah.
Repeat vector and jam.
Okay.
Right?
Yeah.
But then this one shouldn't be two. I mean, the output shouldn't be 2 times NA. It should be 2 times NA and something else, right?
No, what?
Because we iterated over TX of these guys. So this dimension is also should be TX then? No.
That would make sense.
Yeah.
Yeah, that would make sense. But is that a place in the code?
So we are looking at we're looking at the model, right? So this is how it's being called, right? In the model, we go over. We take the output of bidirectional. And then for T and TY, we pass this A and S. I wonder what the dimension of this output bidirectional STM. It's 2 times NS, right? 2 times NA.
Yeah, it should be.
So this one is 64 times what? 64 and 1 or 64 and TX?
Can I see one step attention again?
One
It's just a
step
dot,
attention.
right? Oh no, it's the whole thing. Okay. Oh, okay. Context equals to alphas and A. So where's A?
Alphas and
Oh, A is the input
A, yes, A is being passed here. So A is the hidden state of the output bit.
of shape M TX 2 times. So by the time you get here, it's already M times TX times 2 times.
Yeah.
And that's where
So by the time we get here, so this guy,
which means
output is this, right?
which is kind of weird, but okay. So it gives you the entire history.
Seems like it.
Okay, fine. That makes sense.
Merge mode concatenation, I guess that's why.
Because so for these iron thing in Keras, there is a switch called return sequences. Let me show this. Let me share my screen actually. Okay. If you see my screen, so when you go to like these LSTM models, it has a switch called return sequences. So what that is, what that does is you have the option of outputting just the final thing or the entire
history. Right.
Oh, but this is for output. Oh yeah, we're talking about output. Okay, so return sequences. It's actually set to false.
By default.
So I'm confused right now.
Return sequence true here though. In our definition, it's true.
Oh, it explicitly is actually true?
Yeah.
Oh, okay, then that's it. Oh, okay. Oh, okay. Then that's it. That's basically why you have this extra TX dimension.
Okay. So we have TX dimension of that. Then because we do merge mode concatenate, we have 2 times NAs of them, right?
Right.
And then M is just a batch size. Okay. So that explains this. So when we pass it here, how does that is played in this formula?
So I think it's misleading in the sense that in here, I think what this formula is saying is that this is a formula for only
Context.
Oh no, not really. So A, can you still do okay? Alpha is a scalar times a vector, and you do a sum of many vectors. I think the assumption is that if you do a sum over vectors, it's just basically element by sum, and then eventually the context you get can also be a vector.
Say it again. Sorry.
Okay, alpha is a scalar. We agree, right?
Right. It's like 1 over TX, right? I mean 1 and TX. That's the dimension.
No. Alpha is just a scalar. Oh, okay.
Which one?
Okay, alpha superscript T. Okay, alpha is you have TX of them.
Okay, yeah.
But in this formula, alpha is just a scalar because
Okay.
alpha superscript this thing is basically a scalar, right? And A is a vector of 64.
Right.
So alpha a scalar times a vector of 64 is still a vector of 64.
Right.
And if you do a sum over TX vectors,
Right.
I assume the operation is basically element-wise sum.
Right.
So you end up get the context is still 64 of
Right.
size 64. That's the only way it can make sense.
Okay. So, but I see. So essentially, this is a reduction of that for loop. So instead of saying for A out of all these BIOS-TMs.
Yeah, I think so. In actual implementation, it does things in one go.
Yeah. We just do like matrix multiplication. Okay, got it. The output is 2 and A. Okay, guys. Online, do you have questions? Are you following so far?
Think so.
Willie, do you have a question?
No, I think we got it. Sorry, I just
What? You had a question?
no, I think it's all right. I think it's Xiang was saying it's the alphas and the A. I had it, and now then I think I wonder if I'm second guessing. I think it should be okay. So the context is that's going up to the post LSTM. That should be a vector.
Yeah.
Right?
Yeah.
Yeah. 2 times NA. Yeah, right. Yeah, that gets us all the A's.
Yeah. So maybe we can add little here. Little memo.
I don't see how like anyone could just like breeze through this, and Julian just made it like it feels like this is so easy.
Yeah.
TM reduces.
I just add the comment, change the colors, maybe that. But overall, I think I'm gonna say A from palettes. Yeah. More or less. Right. Okay. So just to confirm, we do that, and then we just go through every single. In your case, J, right? Every single cell in the decoder. We find the context based on A and S. At the very beginning, our S is just the zeros. And in the end, we are actually updating our S. Okay. We find the context, go through all this thing. Okay, so when we do decoder, that implies that everything up to that point has been computed, and we already have it stored in memory nicely, so we don't touch it. We don't change it, right?
Okay, define everything.
By everything, I mean the outputs from bidirectional STMs and even the attentions, like up to that point, all the concatenations being computed. So
yes,
everything
yes. Everything should already be cached and computed.
Yeah, everything up to attention point, up to this point, it has been computed, right?
Yes.
All right. So then what we do, we just find the context for that.
Oh, sorry. A still has to be computed on the fly because A depends on S
A?
T minus 1, right?
No, I don't think so. A's are just outputs, right? Outputs from the BIOS-TMs. From decoder.
Oh, yeah, okay.
I mean, from encoder,
okay.
sorry.
A, but context needs to be computed on the fly.
Yes.
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 Oh, I see.
For each one of these. So that's what I mean. Like up to this point.
I see.
Up to attention point.
Yeah, it shows on the code because A is outside the pre-computed.
Yeah.
Okay.
Yeah.
Okay.
Okay. So we compute the context, and then we pass it to post-activation LSTM. We give it context and the initial state, which is S and C. Okay, initial states are these guys, right? And I'm assuming C is like it's inside, but we don't really care about it because we never really change it. implicitly.
Where is it using the C again? Oh, using C.
This C,
Again, it feeds back into C.
yes, like initial state.
Oh, I see.
So it seems we only, and that was always like my confusion a bit. I think we kind of clarified last time. LSTM, when we talk about RNNs, is just one cell architecture, right?
Yeah, yeah.
That we just keep calling again and again.
Right, LSTM has the extra thing.
Yeah,
LSTM
LSTM.
outputs two things. Okay.
Yeah, but overall, when we define a model, we just define like one cell, right? And then as we actually run through it, we just run through it multiple times. We just call it as many times as we need. But when we display it like visually, we actually unroll it as if they're mini LSTMs, right? But they actually just one LSTM in the memory living, right?
Mhm.
Okay, I just want to clarify that part. Okay, so and that's what we say. Okay, we set up the initial states again like this. I'm assuming there are other ways to do that.
What do you mean?
Let's say you wanna, like, we have in our encoder, we have return sequence true.
Yeah, okay. Here's the thing.
When we
The difference between encoder and decoder, because encoder is very straight up, no attention, everything. So you can just let the Keras facility
yeah
to use its internal for loop
yeah
to get a job done.
right
Because this one has an implied internal for loop. But in here, this is actually a pretty awkward hack, I would say, because I think what it's doing here is essentially you try to do the LSTM thing in one step only.
mm-hmm.
It's like this thing is capable of doing many steps, but you set its step size to one,
Okay, yeah
and then you get the output. That's why you awkwardly have to kind of like set the initial state every time.
yeah
Is that what you mean?
yes, that's exactly what I meant. But if you were to say, okay, this is my LSTM and there's like 10 of them, right? The Keras would automatically say, okay, I'm taking the output of my previous cell and I'm making it as an input to the next one, right? If you say output sequence true.
Can you say that again?
So let's say if I were to define LSTM, let's say I say, okay, here's my LSTM and there are 10 of them, right?
Mhm.
Just like on our encoder.
Mhm.
Then the Keras would automatically say, oh, okay, I'm just passing my C's and S's to the next one by itself. I don't.
It can automatically.
Yeah.
Right now, I think this still goes. Wait, hold on a second. This is an LSTM cell. This is not a.
Yeah.
Can I see the definition? But okay, it is cell, but it is actually an LSTM. So if it's an LSTM here,
Mm-hmm.
that means there's always a loop.
There's always a loop.
Yeah, I think so.
Okay, but the other LSTM that we define, right? Let's say the LSTM of our encoder, bidirectional LSTM. Bidirectional.
Yeah.
But this one, where do we specify how many of them? Like TX of them?
It's implicit in your input. I think when you do input, it always has a time dimension.
Yeah, this one right here, right?
Yeah.
I see. But in this case,
I think in this case, your context must have a dimension of one somewhere, otherwise it wouldn't work. Like the
there's
context.
nothing.
You can verify. Have you verified what's the output what's the dimension of context?
Dimension of context. Oh yeah, we never did that. Context.
Do you have that?
64, yeah. This is where we start, remember?
Okay.
And then the LSTM, this is the our post attention decoder. What the hell is this number? Number of parameters.
So does that imply that so the context in here doesn't have a time dimension? So does that imply that the LSTM can automatically figure out if you do not specify a time dimension, then it's only there's only one step?
Good question. Let's look at
Then-
LSTM cell definition. We have it here.
Its naming is actually misleading, right? Cell should be a cell. Yeah, I was looking at it. I couldn't find anything. Can I see the definition of how we define
Which one?
else the cell, how
Host.
the cell function? Yeah. Okay, so it has this thing called return state, it's true, but nothing else. Return state is essentially like you're gonna return its actual thing or output.
Whether to return the last state in addition to the output.
Yeah, because you have like Python can output like many things, right?
Right.
Output state and then comma. Output, comma, state.
Mm-hmm.
Okay. So I would assume that if you are lacking the time dimension, then it automatically figures out, okay, this is something of step one.
Yeah, that's another way it would work. Don't forget to pass the initial state, hidden state, and aligned one.
Okay.
Because yeah, I think if we were to pass, let's say, oh, I don't know.
So I'm going to source code.
But its dimension is weird here. Why does this one has brackets? The rest don't.
I was going to ask the same thing myself. And also then that column on the last column that it's connected to.
Oh,
Does anybody know how to read that?
sorry, it has brackets because it outputs two things as opposed to one thing.
Okay, so
It outputs like maybe two or three tensors. I think it should output like three tensors.
It outputs three things, so it looks like it gets cut off. It would be nice to know what else is in there.
Three tensors should be, the first one should be the output of LSTM. The second one should be like, the second and third one should be like the two internal states. I think LSTM has like outputs two things as its states. So it's like output, then state part one and state part two.
output
like that.
state part one, state part two. Okay, so what we get is the output, then something in between that we don't care about, and the state. No, the first one is a state. The down one is a context, right?
No, C is the cell state there in the comment.
Yeah.
It says. Oh no! Don't forget. Yeah, no, it is because you're passing it back to itself again with the next iteration.
Okay. So
Yeah.
S is a hidden state and C is a cell state, and we also passing the context. So we're passing three things into this guy. Okay. Let me double check again. I'm a bit confused when we say when we create this LSTM object, right? This is our like initial values, initial parameters. Okay, this is the number of hidden states. I mean, this is the dimension of a hidden state. and return state true. Then when we actually calling it, we're passing the context. Oh yeah, we're passing context as an input, and we're setting initial state to this. Okay, makes sense. And then this guy outputs the S output that we don't care about and the cell state. But is it true that we don't care about the output?
Not really.
Is that output the Y hat?
Yeah, that's what I'm confused about. What this cell is outputting?
I think S should be your output.
S?
Yeah.
Yeah.
The hidden state output. Yeah, the
What is this then?
the documentation, the return, it says returns, and it doesn't tell us a lot. Context vector input of the next.
Where?
Well,
Output.
Okay, where am I? Yeah. Returns output tensors. Like, this isn't telling us anything.
Output shape
Oh.
if the return state is a list of tensors. The the remaining tensors are lost states.
A list of tensors.
Okay, the first tensor is the output, which is the S in our case.
I would think so.
The remaining tensors are the lost states. Each of the shapes, batch size, units. Because our return state is true, right?
Yeah, but like, okay, our thing doesn't output two states. I think it outputs two things. Yeah, here. Am I sharing my screen?
No, you know.
So, if I remember correctly, one thing is this H thing, the other thing is C thing.
Yeah, H is in our case is S, right? That's what we call, yeah.
There are two parts. Yes. But in the diagrams, you see like two things that's hooked to the
Right.
the next thing.
Yeah, and isn't that's H what you're pointing at right now, the hidden state, but then there's this other H coming out on top. Is that simply soft maxed, and that's the what would in other notation I assume that would be the Y hat.
Yeah, that's a mystery. Yeah, that's true. It's the Y hat.
Yeah, and that's what we want for the beam search.
All right, so this we don't care about proper value. Is that the just another output?
Yeah, so then, but it almost as if by the look of it, it almost as if HT, the output is HT, but also the two hidden states, one of them is also HT. So there's a repetition in here.
Yes.
So that's why you see underscore. Like it means like I don't care. This is the same thing with this. Yeah, then that makes sense. Then you feed S back into the next thing. You concatenate them.
Mm-hmm.
One part is the previous state, which is equal to HT. The other thing is C, which kind of corresponds to here nicely because this is our S.
Mm-hmm.
This is HT. They're equal.
Mm-hmm.
So you only need to care about one, and while you also have this additional thing of CT.
Mm-hmm.
Okay, I'm just reading somebody's take on it. Hold on.
Okay, so the outputs, we just append outputs to the out. And our
That's
output,
really weird. I never paid attention, so I don't see it.
Yeah, in our case, when it's return state, the first two S and underscore are exactly the same.
Okay.
And it's just to keep the dimensionality of the returns the same. In the case you turn on the flag for return sequences, then the first return is going to be the list of all the hidden states.
first return would be the list of all the hidden.
Really?
Yeah. Then if we had return
Sequence?
sequences equal is true, then within our code there, the S would become a list.
But when we say return,
Oh.
Yeah, if you want to see my screen.
But then. Okay, I remember. Okay. You mean-
And what I'm talking about, if return sequences is true, you're going to get that if you see that well enough.
Okay.
And then if return sequences is not true, the first one is going to be this is going to be, hold on, stop it.
If you don't return state, then the only thing you return is the output, right? So this thing.
Yeah, this thing and this thing would be the same.
Wow.
In fact, here and here is the same, if you can, because that's the last final output.
Okay. That's
Yeah.
awful API. I'm pretty sure.
Yeah, and then here in this case, it's yeah, the first two are exactly the same. So that's all. Yeah, that's just so it's consistent for its returns.
Fine.
Yeah.
all right. So the just to make sure I understood correctly, the very first one is the S, right? The hidden state.
Yeah. Which screen are we looking at now?
Yours.
Okay. Yeah. So
The second array is
this first one is S. This is the one we don't care about because it's exactly the same as S.
yeah, and that one is a C, right?
That's the C.
All right, and the other one is the return sequences, right? Example.
Yeah. And return sequences, our S is now going to be a list.
Each one, I see. The
And
last one.
the thing we don't care about is the same as the last value that's returned for that's in our S list.
Right.
Yeah, and then this is C again.
Could you share this article?
Yeah, my Slack still isn't working. Does Hangouts?
Yeah. Just post here. I'll post it there.
Yeah. Okay. Hangout chat.
Okay then. We understood that part. And after that is just we passing it through softmax, our output layer, which is dense softmax, yeah.
Yeah.
And then we append it to output and then return the output. Yes, output is output is just an array. Just a list.
Yeah, output is something you accumulate.
Yeah.
Then you end up having 10 things.
Okay. So the model is TX and TY, human vocabulary, machine vocabulary. Dot product, I think, okay, we kind of nailed this one. We understood that. This one is 64 because our hidden state is 64, right?
It's essentially S.
Yeah, of our post-directional, post-LSTM. I'm not sure what the hell is this thing. I think it's just number of dimensions. I mean, number of tunable parameters. And we just don't see the actual shape of our output because it's cut off. Yeah. doesn't do anything. Okay, and then our dense is 11,
Makes sense.
which is from 0 to 9 plus dash, right?
Mhm.
And this is just a softmax. Probability of each one of them. Okay.
I hope I won't forget everything by next week.
If anything, good thing we recorded this whole session.
Okay. Fine.
Do we have a YouTube channel too?
It's not quite YouTube. It's just for our references, just for our
Oh.
records. Yeah, I don't want to like post it. But overall, yeah, I think we nailed it more or less. I think we understand what's happening now. This diagram, hopefully,
Okay, it's
is.
good to go through this. LSTM is so confusing. I hope I won't use it again.
But then I actually saw there's like this model called LSTM-CNN now. They actually combine the thing together for like text summarization.
Oh my god.
This- I was hoping that I don't need to learn LSTM just to go directly to CNN, but I'm like, oh crap, they're actually combining the two to do stuff.
If you use any sequential data, I think you have to use RNNs. So I don't know how
No.
you don't have to.
I try not to use sequential like RNNs or whatever possible because it's slow.
Because it's slow. I
It's
see.
slow.
Fair enough.
The latest, the cutting edge RNN doesn't use any sequential at all. Transformers.
What did they use? Transformers?
Just attention everywhere.
Attention, all you need.
The entire input goes in at once.
Yeah,
And it's fast to compute. There's no like
one by one.
this recurrent thing. Yeah.
I see. The no full loops.
I think the general effort has been towards that direction. It's basically this recurrent thing is kind of this slows things down like significantly. So people like try to get rid of it.
And I'm wondering too, right? Like how scalable is beam search in like productionalized system? Like
Pretty stable.
huh?
Pretty stable.
Pretty scalable?
It's bounded. It's actually bounded by beam size and vocabulary size. Other than that, there's no other.
I guess you can just.
Because I feel it's like a combinatoric problem.
But that's the whole point of beam search. Otherwise, you do exhaustive search. That one is not scalable.
Combinatoric is like you have to exhaust like many different combinations, right? Isn't
But
that
only
slow
two. If your
paced?
beam size in practice, it rarely goes beyond beam size 3. Usually it's beam size 2. If it goes beyond 3, you can probably still somewhat handle it if your vocabulary size is small.
Okay, guys. Online, do you have questions?
No, I'm all good here. It looks like Werner cut out some time ago.
Yeah. Okay.
Now, when is when I'll have dinner with wife?
Yeah, I think so too.
When like
He has a life.
Venus and the like the wife started yelling at him. So, oh, okay, I can't continue what I slept.
All right. Fair enough. Fair enough.
I'm guessing wildly here.
Okay, well, we're gonna wrap up here then.
Yeah, sounds good. So is there anything next week, or is that it for the year?
Did for the year.
Yeah.
Next year. So for LSTM, I think we understand more or less how it works.
I still need to watch a lot of videos and
Yeah.
learn a lot. It's like okay, the last time I think I followed well,
Yeah.
but then this time I feel like it's out of my it's on top of my like over my head.
Yeah. Well, again, good thing we recorded this, so you can always go back and like rewatch it. So for the RNNs, I'm not sure if you guys want to work on a project or anything, you'll certainly welcome to. And if you have any questions, just like ask.
Yeah.
We should be able to help each other with projects. But starting January 1st, like starting next year,
Yeah.
we'll start with the reinforcement learning.
Yeah, it's kind of long already.
Yeah. I guess we'll start with the overview first, just to make sure we're all on the same page.
Yeah.
We'll pick whatever be most interesting, and then we'll just go with that. But I think we'll focus more of a deep
You know what
horror
I'm
than
thinking too?
horror.
Because like I'm thinking, because we're like project oriented.
Yeah.
Right? So like for to add in
Implementation.
implementation, so like just to add more flavor and more interesting things, maybe like for we can actually aim like a capstone day, like a presentation day.
Mm-hmm.
And then so we have, and then we could, and then as like a team to
Mm-hmm.
do that, and then we can maybe invite some maybe potential that could be like a client, right?
Mm-hmm.
So be more like an advertising.
Sure. I think we did it once.
Oh, you did once.
Dlrl presented at Toronto AI. That's and on that occasion, that's like then we got a bunch of new recruits like Austin.
Yeah.
We call
Oh, I see.
it sorry, recruit.
Because like for say like last year we were doing like just for fun, like a small thing, we were trying to do the Kickstarter
Mm-hmm.
data set, and then we just posted that day, presentation day, on Eventbrite, and then someone actually from what like marketing communication institute of Toronto and what chamber of commerce of Sri Lanka actually contacted us. Hey, so they want to come to actually see the thing.
Mm.
So I don't know if that just throw in some
Yeah.
thoughts.
No, this is a really good insight. We'll definitely figure that out. So all many things that are in this workshop are actually feedbacks from the members, like recording this video, like one of the feedbacks, or like presenting at the.
Yeah.
So yeah, we'll do that. Willie, we're not gonna hold you back. I think
Uh,
we wrapped it up. So that was our last session for the year. I'll keep you posted on Slack for the next meeting.
yeah, sounds good.
Person
And
learning.
yeah, I was just looking up here. I'll just really do this real quick. I got to do it again in the chat. Well, I guess it can wait till next year too, but there it is I thought that one might be worth.
Wait, what?
Oh, I see. With the DeepRL, okay.
Yeah. Yeah, when the time comes. Okay. Well, then I guess that's it then.
Yeah, it's perfect. Merry Christmas, Happy New Year.
Yeah, to you too.
I'll see you next year.
Yep. All right, take care.
Cheers.